Hello, hope you're having a great week. Today we're going to start on the first law of thermodynamics. So up until this point, we have covered specific heat capacity, heat transfer, different types of heat transfer, work done on or by a gas, and how that's related to work in a physical sense that we've talked about as far as kinematics go. So today we're going to move on to discuss how the first law of thermodynamics is actually a statement of energy conservation. And then we're going to calculate heat work and the change in internal energy by applying the first law of thermodynamics. So with energy conservation, we know that in an entire system, you can't just lose or gain energy in the middle of nowhere. Okay, so we know that's the law of conservation of energy. And so with this example, we are talking about with or without friction. Okay, so the first law of thermodynamics says that it's a principle of energy that takes into account a system's internal energy as well as work and heat. So overall, if you're gaining kinetic energy, you should be losing potential energy and vice versa. So in this example, this roller coaster is operating without friction. The mechanical energy would remain constant, right? So that's what we talked about the unit previous to this, that kinetic energy plus potential energy should equal the mechanical energy. So if we are losing kinetic energy, you're gaining potential, and the other way around. But we know that real life doesn't exist with no friction. So with friction, the mechanical energy is no longer conserved. The mechanical energy can be transferred to the wheels, the track. It can be lost as sound energy, heat energy. So if both the system and the environment are taken into account, then total energy will be constant. Okay, so with just the system of the roller coaster here, this system would, in a real life situation, be losing energy. But if you're considering the environment that it's in, which is the surroundings around it, then you can account for all the energy. So another example, if you have a balloon here. So we know that weather balloons are often used to determine the pressure at different areas and then help to forecast the weather. So here you have a picture of a balloon. We know that if you have a gas inside a balloon, it's pushing against the latex or the rubber of the balloon outward. So it's trying to do work on the atmosphere. Then we know that the atmosphere is also applying pressure back to the balloon. Okay, so this is going to be an isothermal process, which means that the temperature does not change. So if we have different pressures on the balloon, that can change with the temperature being constant. So what happens to a balloon during a storm? Okay, so the barometric atmosphere pressure will decrease, so the atmosphere is getting less pressurized. That pressure differential causes the balloon to expand because we do have internal pressure that's always doing work towards the outside of the balloon. So the energy is going to slowly be transferred to the balloon as heat. The net result is that the energy transferred out of the balloon as work is matched by the energy transferred into the balloon as heat. So you get these relationships down here at the bottom. So if the work is greater than 0, the heat transfer is also greater than 0 in this case. Energy conservation, we're still talking about your systems in this case. So in these pictures on the right-hand side, the light green color is your surrounding environment, and then the system is anything that's included within that particular setup or that situation that you're studying. So in this case, the work done on a system is negative and the work done by a system is positive. So if we're talking about work and heat, in this case, these are what these arrows are trying to represent here. So let me see. Okay. So work done on the system means that the system's been compressed. So if we are comparing this to a balloon or like a cylinder with a piston inside of it, if the inside of that system is being compressed, the work done on it will be negative. If the work is done by the system, it'll be positive. So these examples, you can see these little minus and plus signs showing up down here. So here we have the work being done on the system, so that means that work was negative. Here you have the work being done to the surroundings or by the system, and that's going to be positive. The next section here is talking about heat being added or removed from the system. So if you are removing heat from your system, that's going to be negative. And if you're adding heat to the system, it's going to be positive. The last thing to talk about here is the relationship to the internal energy. So if you decrease your internal energy, it will be negative. And if you increase internal energy, it will be positive. So as far as the energy and the heat and the work relationship, you kind of have it all summarized in this little table in the bottom left-hand corner. So if you're looking at Q is the transfer of energy, heat energy in particular. So if energy is added or lost to the system, or if no heat energy is transferred, then you're going to end up with a positive or negative value, and the same thing with the work. So with this, we know that energy is going to be conserved in thermodynamic processes. So that means that you're not having an overall gain or loss, because we are going to account for that energy that might be transferred to the environment rather than kept in the system. So according to the first law of thermodynamics, you're going to use this red formula here. So the change in internal energy, which is the delta U, is going to be equal to the energy transferred as heat minus the energy transferred as work. Okay, so because of this, it is very important to keep track of positive and negative values. So if you are transferring energy as heat and it is going to be a negative value, you need to make sure that you're paying attention to that. And these examples here will help you out. Okay, so if heat is being removed from the system, that's going to be a negative value when you put it into this equation. Okay, so if you are, another example could be if work is being done on the system, work will be negative. So you do have to pay very close attention to the direction of the flow of energy with these. So this relationship here just shows this is similar to your different kinds of kinetic and potential and mechanical energy that we talked about before. So your final internal energy minus the initial internal energy will be equal to the change in internal energy. Okay, so you can use these in combination to find just the final or just the initial. And you can do that by using the heat energy transferred and the work transferred. Okay, so a system's internal energy can be changed by both transferring energy as heat, work, or both. An example question of this would be a total of 135 joules of work is done on a gaseous refrigerant as it undergoes compression. So we are compressing a gas in a refrigerant. If the internal energy of the gas increases by 114 joules during the process, what is the total amount of energy transferred as heat? Has energy been added to or removed from the refrigerant as heat? So what we're given here is that we have work being done on the gaseous refrigerant. Okay, so the work is being done on the gas. It's being compressed. So that's a negative value. So we have a negative 135 joules due to the work. The change in internal energy is going to be 114 joules because it tells us that it's increasing. So we need to know how much energy is being transferred as heat. So this picture down here in the bottom corner shows kind of a better diagram description of what's going on here. Okay, so this gas is being compressed. You can see that this is being compressed. It's pushing it down. You're going to have an overall internal energy increase of 114 joules. We know that work is being done on that system because it's being compressed, but then we have to figure out how much heat is that going to be transferring out. So starting with our first law of thermodynamics formula, we know that the change in internal energy is going to be equal to the heat lost, or the heat transferred, I should say, minus the work done. So here we have the change is 114 joules, set equal to the heat transfer minus negative 135 joules as the work. So overall, we end up with negative 21 joules of energy, and we know that that's being removed because it's negative. Okay, so that all goes back to the slide that's prior to this one that talks about the relationship between gaining and losing energy and whether those are positive and negative values. Another example here, we have a Steens Boiler, completely converts 155 kilograms of water into steam. This process involves a transfer of 3.5 times 10 to the 8th joules of heat. If steam escaping through a safety valve does 1.8 times 10 to the 8th joules of work expanding against the outside atmosphere, what is the net change in the internal energy of the water steam system? So again, I have another diagram down here at the bottom. You have work being done by the gas onto the atmosphere, and you also have heat being transferred outside of the system. So the work being done is 1.8 times 10 to the 8 joules, and we know that the heat being lost is 3.5 times 10 to the 8th joules. So we need to find the change in internal energy. So again, we're using the same formula, substituting in our values for work and heat transferred, and you come up with an internal energy change of 1.7 times 10 to the 8 joules. So the internal energy in this system has increased. This goes along with our cyclic processes. So a thermodynamic process is in which a system returns to the same conditions under which it started. Okay, so all in all, if you're including the environment as well, you should have no net transfer of energy, right? So the net transfer of heat should be equal to the net transfer of work. So as you're in, one is incoming, one is outgoing. So the final and initial values of internal energy are the same, and the change in internal energy should be zero. Okay, so it's going to resemble an isothermal process because all of our energy that's transferred as work and heat in the temperature should remain the same. So if you look at the diagram on the side, the circle with the E is going to be our system. So if you have a source of hot temperature coming into the system, so you're adding heat, so that's our Q1. So we're adding heat into the system. You're also losing heat and work at this point. So you're going to lose heat to your cold, your sink. So you're always going to have a hot and a cold, different. I can't think of the word. So you're always going to have a hot area and a cold area. Okay, so with a heat engine, a cyclical process, you're also going to lose work due to the change in energy. So with a heat engine, you can use heat engines to do heat and work. Heat engines are devices that use heat to do mechanical work. So you're going to do work by transferring energy from high temperature substances into low temperature substances. And in the process, the net work will equal the energy transferred from high to low. So this formula will be what we use for that. So if you want to figure out the net work done by a heat engine, it's going to be the difference between the high temperature or the hot heat transfer coming in minus the heat transfer going out to the cool area. Okay, that's going to be it for today. Next class, we'll get started with the second law of thermodynamics. But for today, you do have a couple of practice problems to do, so please get those done and let me know if you do have any questions.